Well, here we are at Chapter 9, the overview problems for Chapter 9. First of all, the idea of Chapter 9 is that we're testing claims, but it's going to be about two means, two proportions, or two standard deviations. Then the last idea is that we've got paired data, which I'll get to in the last problem. So this first one is going to be about two means. So we're comparing two quarterbacks from the NFL, Peyton Manning and Drew Brees. And to make the sample size large enough, I went over the last two seasons. So my data, let me just collect that right here. For Manning, I've got n equals 32 games. And he averaged 8.2 yards per play, with standard deviation equal to 2.3. And then for Drew Brees, it's also n equals 32 football games. X bar, oh, there it is. Drew Brees averaged 7.8 yards per play, with S equal to a 2.1. So as far as the X bars are concerned, Manning is just slightly better, an 8.2 compared to a 7.8. But of course there's variation with each player, so you're not guaranteed to get 8.2 yards per play out of Manning every play. Okay, so the claim is the two players are equally good. So we're saying that mean 1 equals mean 2. Whenever you have the choice as to who's going to be group number 1, it should be the one with the bigger mean. So Manning is going to be group number 1. Brees is going to be group number 2. So the claim is that mean 1 equals mean 2. H1, of course, cannot have equals, so this is going to be a not equals, making this a two-tailed test. H sub O always has equals. And then we need the t distribution. Since this is S, then it's going to be a t distribution. So that's table A3, and for that we need degrees of freedom. And the degrees of freedom, we use the smaller of the two degrees of freedom. This one would be 31, this one would be 31, so we don't have a choice, it's going to be 31. And then alpha equals 0.05 because I'm using 95% level of confidence. So we'd have these two tails, and then I need table A3. This critical value is going to be negative, this critical value is going to be positive. So table A3, that's going to be the middle column because it's two tails with 0.05, and then degrees of freedom 31, it actually does occur in the table down here. So 31 going across to the middle is 2.040. 2.040, negative 2.040. And then for the test statistic, t equals, here's a good place to use the calculator. So I go over to stat, and then tests, and look for a two-sample t-test. So that's number 4. Two-sample t-test. Then we need to tell it the information for these two football players over here. So number 1 has an average of 8.2. S is a 2.3 based on 32 football games. Then this one is 7.8 with S equal to 2.1, also based on 32 football games. And then for this part that says pooled, just say no, do not pool it. And then calculate. So it turns out that it's a 0.727. That, when you look at these values, actually lands in between although slightly to the right, but it means that we failed to reject. So in other words, we did not prove anything. Cannot prove that one player is better than the other based on these statistics. Okay, so there's one other thing that's covered, and that is confidence interval. Since we're using the calculator, it is not much work at all. So what's the confidence interval? In other words, if you were to subtract these two means, so an 8.2 subtract a 7.8, what that would mean is that Manning is 0.4 better, or his average for those games was 0.4 better than Breeze. But in general, what would it be? So mean 1 minus mean 2, if you were to look at their whole lifetime worth of football games. So, since we're using the calculator, you just go over to tests. You know, I wish they would rename that because only part of it's tests. We also have intervals. Anyway, I'll include in my next letter to Texas Instruments. Anyway, we're now looking for 2 sample, and it's a T interval, so it's actually the 10th one on the list. And the calculator is nice enough to remember the information, just move down, and 95% level, yes. Pooled, always say no, and then calculate. So on the right-hand side, it says that it's a 1.501. On the other side, it says negative 0.701. Having a negative on this side and a positive on this side is the same thing as getting this. Fail to reject, we cannot make a conclusion. Because what this is saying is, when you subtract the 2 players, it could be that you get a positive number. Well, the only way you can have a positive number by subtracting is if you have a big number minus a small number. That means whoever was group number 1, Peyton Manning, he's better. And he's better by almost 1.5 yards per play. But then this side says it's negative. The only way you get a negative is if you have a smaller number subtract a bigger number. That means the second player is better. So this side is saying that the second player is better. This positive side says the first player is better. Also, the number 0 is in between these two. And if their difference was equal to 0, then they're the same. So this side says Manning's better. This side says Breeze is better. And when it's equal to 0 in between these two, then they're the same. Thus, we cannot make a conclusion. So when this, for example, if this was like 5.7 and it landed over here and we did prove something, then this would have been a positive number and this would have been a positive number, and we would have said for sure Manning is better. But with this data, we can't conclude. Okay, so this one is actually going to be pretty similar to the last one, a little extra practice. So I had pre-calculus, and there was n equals 32 people by the end of the semester. They averaged 76.7 with an S of 15.7. And that is pretty much an average pre-calculus class. On the other hand, I had a very good calculus class, n equals 40, because only one person dropped. Their average, 82.8, with a standard deviation of 11.3. So now, who should be considered group number 1? You're right, the calculus people. This one has the bigger mean. This is going to be group number 2. So then the setup is going to be the same as last time. Claim is that, at least I think I better double read it. Tesla claimed that no. Actually, I said that the calculus class did better. So the claim is going to be that group number 1 did better than group number 2. And in this case, bigger than would be better. H1 can't have an equals, so it has to point to the right. It's going to be that mu1 is bigger than mu2, so that's right tail. And then h sub o says equals. All right, now for the bell-shaped curve. So we would have a t distribution. This one is right tail only. We're using 95% level of confidence, so this is 0.05. We would have one critical value to look up, and we would need to use degrees of freedom. So then you use the smaller degrees of freedom. So this one would be at 31, this one would be at 39, so we use 31. So table A3. And which column to use? Well, first of all, it's just one tail, and in that one tail there's 0.05, so this is the column. And then move down to 31. So here's 31, here's the fourth column, so it's at 1696. 1.696. And then for the test statistic, I should have written, no, this is table A3 we're using. So it's going to be the 2-sample t-test, and I need my sample data over here. So let me see, group number 1 is these people, so that's going to be 82.8 with S equal to 11.3 based on 40 students. This is a 76.7. 15.7 is the standard deviation based on 32 students. And then this should be pointing to the right, and this pooled should say no. So calculate. A 1.848. Notice also that the p-value is 3.5%, and since that's less than 5%, we're going to reject h sub o. Also, if you use the test statistic, it was a 1.848, and that goes past a 1.696, which means reject h sub o. Which really means we're rejecting this equal symbol right here. The two classes are not equal. Then, is the claim true? Is this class better? Well, since this landed to the right, that means that they have a bigger average. So the claim is true. That calculus class was better than the pre-calculus class. Now, I wanted to also look at the confidence interval, because since we did actually prove something, then the confidence interval should have a positive number on one side and a positive number on the other side. Let's verify. So go over to this, and we need, what is it, the 10th one? 2-sample t-interval. The numbers should still be in the calculator's memory. Double check that those look okay. Yeah, that looks right. And go down here and tell it we're using 95%, pooled no, calculate. So both numbers should be positive. Uh-oh, what happened? When we get one side being positive and one side being negative, that's the same thing as saying fail to reject. So this side is saying that the calculus class was better by 12 points. This side is saying the pre-calculus class is better by half a point. So in other words, according to this confidence interval, we can't make a conclusion. So why is it that this one made a conclusion and said that the calculus class is better, but this one doesn't? Well, the reason is this is one-tailed. So this has 0.05 as its cutoff for the one tail. But this one is two-tailed. So the 0.05 had to be cut in half. Half of it, 0.025, put on this side, and the other half, 0.025, put on this side. That's the reason why the two things are not agreeing. They're not both using 0.05 for each tail. This one is using 0.05 for this right tail. This is using 0.025 for this tail. Well, let's see. if on this method, the critical value method, if we would use 0.025, that would mean use this. For one tail point, use 0.025, go down to 31, and then it would be a critical value of 2.04. So if we had this as a 2.04, then does this go past a 2.04? No. So then we would have gotten failed to reject. So in many places where statistics is used so that people can't do this and sort of get away with something, they let's say they say, you know what, I want to make sure it's reject, so I'm going to put 0.05 here instead of 0.025, and then look, I got it to reject. The claim's true. Those calculus people are so much better. Well, in medical journals and things like that, so that that doesn't happen, what they will do is just report the p-value. So they won't even give you the test statistic or the critical value. They will just report when you do the test. Let me do the test again. They will just give you the p-value. Here's the p-value. You decide. So if you make a conclusion, there's 3.5% chance of being wrong. It's up to you. You make a conclusion. Are you willing to live with 3.5% chance of being wrong? You know, if it's something like, should I buy Coke or should I buy Pepsi? 3.5% chance of being wrong. Yeah, that's okay. I can live with it. If you're going to be cutting into someone's brain to try and take out a tumor, 3.5% chance of being wrong is really not acceptable. So anyway, that's one reason the p-value is used. Next up, something about proportions. So we've got these two basketball players, Marco, okay, I don't know how to pronounce his name, Bellinelli. That's Marco. I'm going to call him Marco. And he has made, as of January 2014, he has made 61 out of 121 of his three-point attempts. And then Andre Iguodala of the Golden State Warriors. So Andre here. You know what? I watched the Golden State Warriors last night, and I listened how they pronounced his name, and they changed it every time. Iguodala. Anyway, x equals 32 out of n equals 82. So who has the better percentage? We need to divide, or in other words, find the p-hat, so we can decide who's going to be group number 1. So it's just the number of successes divided by the total. So 61 out of 121 compared to 36 out of 82. So those are their proportions. So p-hat for Marco is 0.504. So he's going to be group number 1 because that's the larger. The other one is 439. So for Andre, it's 0.439. Okay, so there's the data. Now the claim. Test the claim that Marco is the better player. So the claim is that P1 is a better percentage than P2 in general. So that means that H1 is going to be pointing to the right, and then H sub O will have that P1 equals P2. And since it's about proportions, then it's going to be the Z distribution. We would have alpha equals Let's see, on the last problem I got into a little bit of trouble because when I made my confidence interval it used 0.025 and 0.025. So for this one, although it doesn't say, that means I'm supposed to use 95%, but I want to avoid that problem of last time. So what I'm going to do is, yes, make it a right tail, but I'm going to use 0.025 so that my results from this test will agree with my results of the confidence interval. All right, so if that's 0.025, and then we need the z-table. And if this side is 0.025, then the other side, 1 minus 0.025, is 0.975. So we need to look through the table and find what's closest to 975. And it happens to be right here. If you look over to the left, it's going to say 1.9. And then if you look up, it's the 6. So it's 1.96. So the critical value, 1.96. And then for the test statistic, it's going to be a z-test. Everything about proportions is z. So we've got it right here. 2 proportions z-test. So the first person, number 1, has 61 out of 121. The other person has 32 out of 82. And then we need it pointing to the right, and that's all you have to tell it, then calculate. So it turns out that it's a 1.598. And a 1.5 does not go past a 1.9, so it's going to be fail to reject. We cannot make a conclusion. And since we got no conclusion for that, when we make the confidence interval, one side should say a negative number, the other side should say a positive number. So that confidence interval is going to be for the proportions in general, the difference between those, and then make the interval. So down here to intervals, it's got to be 2 proportions, so it's, what's that, the 12th one in the list. The information is still there. We're using 95% level, that way it's going to take 5%, put half of that, or 2.5% on this side, 2.5% on the other side, which is what I did for this one. And then calculate. Sure enough, one side is negative and the other side is positive. So negative 0.024, and the other one is positive 252, which is another way of saying no conclusion. Well, we've got 2 to go, so let's get to it. Now something about standard deviations. So it's the same information that I had before. So there's the pre-calculus, n equals 32 students. This question is about the standard deviation, so you don't even need the mean. Ignore the averages. All you need is the S. So S equals 15.7. Then for calculus, n equals 40 people, and S equals 11.3. And then, who's going to be group number 1? You're right, this time it's pre-calculus because they have the bigger standard deviation. Alright, then the claim is, test the claim that the 2 have the same standard deviation. So the claim is that standard deviation for group number 1 equals standard deviation for group number 2. H1 can't have an equal, so it's going to say not equals, which then tells me that there's 2 tails. And H sub O just does the same thing every time. And then for the distribution, well, let's see. When it's about standard deviation, there's 2 possibilities. It could be chi-squared, Or, if you look at your formula card, when you've got two populations, you've chosen that group number 1 is bigger than group number 2, then here's the test statistic. It's F. So the F, it's just going to take sample standard deviation number 1, square it, and then divide by this one squared. So that's the test statistic. That F is equal to the bigger standard deviation squared divided by this one squared. And because we put the bigger one on top, it's going to make this land to the right. So this is a right tail only. So this will be 0.05. And I can't find my table A5. I think I have it right here. Okay. So with table A5, you'll either need to have the book, download it from the internet, or I don't know, look on my website. So with table A5, you've basically got two choices. The right tail, notice that it's a right tail only, could have 0.025, or if I flip the page, it could have 0.05, which is what ours has. Then with the way that table A5 works is you have degrees of freedom number 1, you look it up over here. When you find it, you then find degrees of freedom number 2 over here. And then you find out where those two meet. So we need degrees of freedom number 1 and degrees of freedom number 2. So looking at this, degrees of freedom number 1 is equal to 31. Degrees of freedom number 2 is 39. And like with all of these tables, if they don't have exactly this or exactly this, you use whatever's closest. So notice that when you look at degrees of freedom number 1, it only goes up to 9. Well, you then just move the table down and it starts again at 10, 12, etc. So we were looking for a 31. There was no 31, but there's a 30. Then along the side, we need a 29. No, we need a 39. So this one was supposed to be 31, but they don't have it. We're going to use 30. And then along the side, if I can get it on the screen, you go down, and I would look for 39, but they don't have 39, so I'm going to use 40. So if you go to where 40 is, then that's 1.7444. 1.7444 is the critical value. This one I had to use 30, and this one I had to use 40. Alright, then the last thing is we need to do this formula ourselves. It's not in the calculator as one of those tests, but that's easy enough. It's just dividing two numbers. 15.7 squared divided by 11.3 squared. Does that go past 1.7? Yes, it does. We actually proved something. So since it goes past here, we then say reject H sub O. The claim was that they're equal, so that means the claim is false. Because we just rejected equals right here when we said reject H sub O. So the claim is false. So we're talking about standard deviation, which is consistency. That means that this class actually has a bigger standard deviation, which means less consistency than these people. And then for the last type of problem in this chapter. So it is two populations. So here's one population. These people, when they started a weight loss program, here's their weights. Then here's the same people after 6 weeks. So the first thing that we have to do is find the differences. So in other words, how much weight did they lose? And there's two ways you could do this. One is the long way, like I'm doing right now, which I'm only going to do part of. And you just subtract. So this person, if you subtract, lost 8 pounds. This person lost 7 pounds. This person, 2 pounds. And then 11 pounds, 0 pounds, 9, 6. Don't you just love math? 4, 8, 6, 11, and 5. And then what you need to do is type those numbers in a list, the 8, 7, 2, etc. Or here's a faster way. So first of all, before turning on the camera, I type those numbers into the list 1 and list 2. And then what I would do is just go to the home screen, so just quit. And so under the numbers 1 and 2 and 3 are the names list 1, list 2, list 3. So you just have to put second, number 1, minus second, number 2, oh, sorry, I hit the wrong one. Second, list 1, minus list 2, and then store that in list 3. And store is right over here on the left. So store that, second, list 3. And then you'll see the numbers. 8, 7, 2, 11, 0, 9, etc. And then what you can do is tell it, stat, find the mean and standard deviation. So this now needs to be list 3 for those differences. So for the D's, x bar for the D's is equal to 6.417. Standard deviation for the D's is equal to S. Sorry, it's off the screen. 3.343. And then the claim is going to be about the mean for the D's. So test the claim that the weight loss program is effective. So what does it mean for a weight loss program to be effective? Well, that means that people are losing weight. For example, was it effective for this person? No. If there was a person that gained weight, like for example, if somebody went from 190 to 195, then when I subtract, I would have gotten a -5. So if it's a negative, they're gaining weight. If it's a 0, they didn't lose any weight after 6 weeks. So those are not successes. It's effective when it's a positive number, when D is a positive number. So when the mean is a positive number, that means it's effective. They are losing weight. So then H1 would be the same thing. Pointing to the right means it's a right tail. H sub O would have equals 0. And then we're back to the good old T distribution from when we very first started hypothesis testing. So it's just going to look like this. It's going to be right-tailed. T means table A3, which means we need degrees of freedom. So the one thing I didn't write down is what was the sample size. Sample size was 12. So that means degrees of freedom is 11, and then use alpha equal to 0.05. And then we need good old table A3. Come here, you. There you are. So let's see, it's one-tailed, but it's 0.05, so that's this. And then degrees of freedom was 11, so we're working with 1796. Critical value is 1.796. Then it's just a straightforward t-test. So the test statistic t equals so it's going to be the t-test. And what we could do is even tell it use the data that's in list 3. Or you could just type the mean and standard deviation. And then this is saying, if you look at h sub o, what number is it? It's a 0. And then this should be pointing to the right, so that it's a right-tailed test. And then calculate 6.650. So does a 6.6 make it past a 1.7? Yes, by a long shot. That means we actually proved something. Yippee. So reject h sub o. And so is it positive? So is this a positive, excuse me, so this says the average is positive. Is this a positive number? Yes, it sure is. And what this is saying is that they're losing almost 6.5 pounds. So is that considered effective if people are losing 6.5 pounds? Yes, definitely. So the program is effective for losing weight. Okay, until next time.